Hi, my name is Hemang, and I'm a software developer at Amazon.com. I specialize in building machine learning solutions for identifying and detecting intellectual property infringement. So today, I'm here to give a talk on machine learning approaches for IP protections in cloud environments. Let's go over the agenda for the presentation. We'll start off with discussing what are the key challenges or problems that when it comes to IP protection. Then we'll go over some of the techniques and methodologies to identify use of IP. Then we'll go over some of the ML models and techniques that you can use to detect illegal or violation of IP use. Then we'll talk about how to make these systems more scalable by deploying them in cloud. And finally, we'll go over how we can use Golang to improve performance of these ML pipelines. Intellectual property theft is a huge issue to companies. It's estimated that globally, companies spend almost $600 billion every year fighting IP theft, and 60% of these cases are all digital. Predominantly, this industry of intellectual property protections has been very manual, but with the advent of machine learning systems, we've been able to automate a lot of the processes and improve detection. ML systems are just as good as humans when it comes to identifying patterns or repetitive patterns. And that's one of the major reasons why we've been able to automate a lot of these. So what are some of the critical challenges in IP protection and how can ML help solve these challenges? As I just mentioned, automation was one of the key issues. This industry was predominantly manual and a human could take only 100 to 200 cases in an hour. But with ML systems, process and identify almost 100,000 occurrences of IP infringements within an hour. One of the key problems for this industry is pattern recognition, because when it comes to IP protection, you need to be able to identify use of logos, copyrights, and such protected assets in different places. So machine learning is a really good use case for machine learning. With the advent of convolutional neural networks, pattern recognition became very easy for ML systems. And with the recent advancement of the transformer architecture, of identifying nuances or identifying edge cases when it comes to pattern recognition has just become even more easier for machines. The other problem is how to make it more scalable, right? This is where cloud comes in. Cloud-based ML systems can handle almost like a huge volume. It can easily handle traffic spikes and whatnot. And with the recent advancements that we're seeing when it comes to training and inference of a lot of GPU-based chips being built, which are very efficient. It can help train ML models in shorter time. It can handle very high throughput inference volumes. So with that, we're seeing the costs almost reduce 20 to 30% year over year to deploying ML pipelines. So let's get into the process of IP protection. I would say IP protection is a two-step process. Step one is discovery and step two is detection. Discovery is basically searching or finding the use of your IP, and step two is detecting if this use is indeed fraudulent or not. Let's focus on the search part first. There are two foundational search methodologies. One is keyword-based search and the other is embedding-based search. Keyword-based search is basically searching for use of keywords. It's predominantly a text-based search mechanism where you try to search if certain keywords are present in a subset of your search space. So say you have 100 million products or 100 million web pages or 100 million books, and you're trying to search for the trademark Nike being used in which of these web pages does mention Nike. You could employ keyword-based search mechanisms to identify the pages which use the term Nike. The plus point of keyword-based systems is that they offer high throughput. The compute that it uses is minimal or lesser compared to embedding-based searches, and that's why you can search across hundreds of millions of documents within a fraction of a second. On the contrary, the drawback is that it lacks context awareness. It would, given that it is very rudimentary and string-based search operation, it does not actually understand the context or the meaning behind the search query and the meaning behind the use of the search term in the documents that it is searching. So that's where embedding-based search comes handy. Embedding-based search is a lot more context-aware search, where you employ different machine learning models to convert your search query or your document into embeddings. And these ML models do the job of extracting context from your text or image and store these contexts in the form of vector representations or numeric representations. So because of such mechanisms, it is able to gather context out of your query and do a much more targeted search. But the drawback of embedding based search is that it uses a lot of compute. So it's hard to make it very scalable. If you want to use embedding based search mechanisms on a billion scale, your queries tend to perform much more slower than keyword based search. The gold standard generally is to use a hybrid search solution so that you get the best of both worlds. You get the high throughput advantages from keyword based search and you get high precision related advantages from embedding based search. What we generally do is first employ keyword based search to narrow down your search space, and then when you have a base, you use embedding based search to just give you results that are highly accurate to your search query. If I were to give an example, say you have 500 million web pages, and from these 500 million web pages, you only want web pages which have images of Nike Air Jordans, the shoes. What you can first do is first use keyword-based search to find all the web pages that have mention of the term shoes or any of its synonyms. And by doing this, you might reduce your search space from 500 million to just 10 million web pages which have mention of the term shoes. And then you do a embedding based search where you generate embeddings for the images of Nike Air Jordans, and you then generate embeddings of these 10 million web pages and see which do a sort of a similarity search, a KNN similarity search, to identify which web pages from these 10 million actually have the use of a shoe which is very similar looking to Nike Air Jordans. So with this, you might be just left behind with 2,000 or 3,000 web pages that have use of images of a shoe that are very similar looking to a Nike Air Jordan. Now that we've seen some of the search techniques on how to shrink your search space or just find relevant documents from your search space, let's look at some of the techniques on how to detect IP infringement. We'll look at two domains broadly. One is image-based IP detection and one is text-based IP detection. Let's look at image-based IP detection first. There are three main use cases or problem statements in this category. One is the identifying use of logos in images. The other could be identifying use of visual trademarks or copyrights. And the third is detecting manipulation of a copyright to a certain degree. So logo detection is basically identifying use of brands' logos in images. There are a few ML models that are doing really good job in this space. One of the state-of-the-art models is the YOLO family of models. YOLO stands for You Only Look Once. These are predominantly object detection models, but it's really easy to pick one of the pre-trained YOLO model and fine-tune it for a data set that only contains annotated logos in images, and the output model that you get after fine-tuning is a model that easily detects a logo in an image when you pass an image to it. And these are very lightweight models, so you can blast it up at 20,000-30,000 transactions per second, and you can really get good throughput out of these models for lesser costs. These models generally have a high accuracy, upwards of 96-97%, and they allow for high throughput as well. When it comes to identifying use of a brand's or an artist's copyright, the VID, which stands for Vision Transformer models, or the VLM, visual language models, has been really useful in these domains. These are predominantly multimodal models where they take an image, gather as much as information as possible from this image. They also convert the image into textual format and then try to understand what is there in this image. So these models really help identify use of copyrights such as fictional characters being present in content, and these models are much more larger than some of the logo detection models such as HEOLO models, and therefore they take much more time for inference than the logo models, but these have really high precision and low FP rates. The third problem, image manipulation, is a much more simpler problem than the other two, because this is the solution that you could employ is very simple. You just use some image-based embedding models to generate embeddings of your artwork or your asset, and then generate embeddings of other images that are there on the internet and see how similar are these two vectors. If the cosine similarity between these two vectors, your vector and the vector of image that you fetch from the internet, are very high, then it means that it's a very similar looking image or very similar looking artwork with just a few nuances. You don't even need a multimodal model for such use cases. Just a pure image-based embedding model does the job. Next comes text-based IP protection. So let's talk about text similarity detection first. Just like image-based embedding models, there are a lot of text-based embedding models which have been trained on the entirety of the dictionary and the probability of occurrence of every word in the dictionary to rank different words in the dictionary and generate embeddings for any given text phrase. These models can be pretty useful in generating embeddings of a text phrase and seeing if another phrase out there in the search space is very similar to your trademark text. Some of the use cases where this comes in very handy we see in the industry is for plagiarism check, for checking if research papers are very similar of a research paper in the past, or text-based original content. For example, books of authors, if they're being infringed on text of another book that has been launched or released in the past. The other use case is brand misrepresentation. So what in the retail industry, what we see is that once a brand becomes famous, there are a lot of knockoffs that come into the market which sound very similar to this brand. Some of the famous examples are Adidas and Ibas, where the second D is converted to a B just to have a difference in the name, but have the design language and everything that's very similar to Adidas. And some of these NLP techniques where you can normalize text using a lot of different tokenizers and a lot of different packages that are given out, a lot of Python packages that are available to normalize your text and then perform a similarity search, is helpful for such use cases. And then comes the LLMs that we've seen in the recent past, where these are multilingual. It can perform similarity search across languages. So it has a machine translation layer which normalizes text before generating embedding into a single language. Using the same IP or the same trademarks, but in a different language, can also be now identified using such models. Deploying ML pipelines in cloud helps reduce costs by a large percentage, because cloud is generally a multi-tenant environment where multiple organizations or multiple clients deploy their workloads, and you only pay as you need. You only pay for the services or for the duration that you actually use an instance or a cloud resource. Given that these are huge data centers, they offer really high availability with a lot of replication factor in place, such that your instances are deployed and replicated in different zones in multiple data centers across the world to offer high system availability. The use of GPUs is a lot more efficient when it comes to cloud. Also, having our own GPUs on an on-premise system is a very expensive is a very expensive affair, especially if you are underutilizing the GPU. If your workloads aren't continuously high or maxing out the GPU, then you're paying a lot of money for the GPUs when utilizing very less. With cloud, this becomes cheaper because there are multiple tenants and everyone reuses the same GPU when required. Let's look at some of the techniques that one can use to optimize or improve performance of ML systems or ML models. There are four main approaches that we look at: model parallelism, data parallelism, model sharding, and quantization. So model parallelism is something that you can use when your models are very large, where model might not fit on a single GPU instance. So what you do is you split the model. There are certain layers. You split the model horizontally across layers and deploy the chunk of the model on different GPU instances and invoke each instance one of the other, where the output of the first instance goes as the input of the other instance. And then you can reuse the first instance once it has finished processing for the next request. So this is where you can split your model across multiple GPUs. And this is generally useful when your models are very large and you want to use smaller GPU instance sizes. And of course, when the model is built in such a way that it allows for splitting up the layers of the model. Then comes data parallelism. So this is useful when you are underutilizing a GPU. It is possible you can deploy multiple instances of a very small model on the same GPU and or across different GPUs as well, and batch your data and invoke it across all the different instances for inferences. This helps boost the throughput as well, because now you are utilizing your memory and compute more efficiently. Third comes model sharding. So model sharding is a little similar to model parallelism, but works a bit differently. In model sharding, you vertically split the model into a number of pieces when it's hard to deploy the model on a single instance because it's too large. So you shard the model in such a way that your input data also can be sharded when you want to invoke the model for inference. So the model, which is now sharded into 4 or 5 different pieces, are deployed on different instances. And when you invoke the model, your input tensor also can be broken down into corresponding pieces and sent to the respective shard. And the output can then be concatenated to generate the response. The last one is quantization. So this helps lower the size of the model by compressing the weights of the model. So say you compress or convert the weights of the model from a floating point 32-bit to a 16-bit floating point. You reduce the size of the model and also the memory required for inference of the model. So let's talk about how Golang can be helpful in ML pipelines. So before we get into that, some overview about Go. It's an open source programming language developed by Google. And the best part about it is its speed, because it compiles to machine code. Its performance is similar on the likes of C, C++. It's really fast compared to programming languages like Java, which have a lot of overhead because of JVM or Java virtual machines. It's very cloud native in design because it seamlessly integrates with Docker, Kubernetes. It's really useful to build containerized APIs or services, basically microservices. And it offers high concurrency with built-in Go routines and channels, which enable multitasking and help build high throughput pipelines. So specifically when it comes to ML pipelines, the biggest use case or biggest place where Go could be useful is building high throughput streaming pipeline, where you have incoming data in a streaming fashion, where millions of records are coming in every minute or every hour. You use a sort of a Kafka plus co-consumer setup to react to these incoming reactions or incoming signals and invoke machine learning models So you could use a gRPC client to invoke remote procedure calls and go to a PyTorch or a TensorFlow backend. It really helps convert a lot of asynchronous applications into synchronous or real-time processing applications because of its throughput and low latency capabilities. And it's really easy to deploy these services on cloud because of its integration with Docker and how we can containerize these web services and deploy in containerized web services platforms such as ECS provided by AWS and so on. Looking ahead, there's a lot more to be achieved in this space of IP protection. There's a lot more automation that is required and for which there is hope for. Where AI is or machine learning is able to identify most of the patterns, but the novel approaches taken by bad actors are still being identified by humans. There's research being done on how to use blockchain and blockchain-based ledgers for verification and determining ownership of IP assets. And with time, we are seeing adaptive AI systems where we use a lot of these LLMs to make them self-learn and help them identify the new patterns that bad actors can develop over time without a human having to tell them what to do or pass training information. Thank you so much for your time. Hope this was an informative session.